Here we are, we're going to do a sample problem on mechanical energy. Our problem here is a 1 kilogram ball is dropped from a height of 20 meters. We're going to analyze the mechanical energy at a couple of points, 20 meters, 15 meters, 7, and right before it hits the ground, effectively 0 meters from the ground, but not while it's on the ground. Now, let's remember our equation for mechanical energy, or total mechanical energy, is that it is all of the potential energy. In this case, it's going to be gravitational potential energy added to all of the kinetic energy. All right, and remember that mechanical energy stays constant throughout, and we're going to get back to that again. If we break these down, gravitational potential energy, the equation for that is m, which is the mass of the object, g, 9.8, h, the height relative to a reference point, or delta y, and kinetic energy is 1/2 mv squared. Okay, I'm going to maybe, I just want to maybe redo this 1/2 so it looks not like the mv is on the bottom. Okay, so at time A, we are at a height of 20 meters and we are not moving, as we could see by the dot next to our ball, which looks like a blob, but that's okay. So in scenario A, we know, first of all, that our velocity, the object is not moving then, is 0 meters per second, which effectively turns our kinetic energy, if we are doing 1/2 mv squared, the mass is 1 kilogram. It's already in the right units. If it's 0 meters per second, for our velocity, even if we square that, we get no values. Our kinetic energy is 0 joules. So all of our mechanical energy is going to be in gravitational potential energy, and we know the mass, we know gravity, we know the height, so we can find out the mechanical energy for this system, which is going to be the mass, 1 kilogram, times gravity, 9.8. In this case, the units for gravity are going to be newtons per kilogram. You could work that out with F equals ma. There, newtons per kilogram is equal to meters per square second. So the acceleration due to gravity value here is the same, even though the units are different. And then the height in this first instance is 20 meters relative to our reference point. So we can calculate our mechanical energy for the system as 1 times 9.8 times 20, which ends up being 196 joules. Okay? And so we know that is not only the mechanical energy for the entire system, but that is also the potential energy, gravitational potential energy, and maybe I'll put at time A, because all of our energy comes from gravitational potential energy. Now let's talk about, let me label the rest of these. We'll color code B, C, and we can do D. Here. At time B, our height is now 15 meters from the ground. Our mass is still 1 kilogram. Now, it's moving, so that obviously means that there will be some sort of velocity. Our velocity will not be 0 anymore. It will be falling, but it's still a distance from the ground, so it will still have some gravitational potential energy as well. And if we think about a pie chart here of our mechanical energy, I can draw one for time A. 100% of our energy will be gravitational potential energy at time A. At time B, however, it might be that, I'm making a prediction here, maybe 3/4 will be gravitational potential energy, and some quantity will be kinetic energy, but not a lot. And we can actually calculate this, but I'm just making a prediction of what that will look like, because it is falling, but it is still relatively high up. So, how do I go from one to the other? Well, I have a height and a mass. I can calculate my gravitational potential energy at time B with my mass, the 9.8 for gravity, and the height of 15. And now if I put that into my calculator, I get a value of 147 joules as my gravitational potential energy. How can I get my kinetic energy? How can I get its speed? Because I don't have either of these. The key here is that mechanical energy stays the same the entire time. So if I calculated a mechanical energy of 196 joules at time A, that mechanical energy must stay the same throughout. So my total mechanical energy is 196 joules. And I know that mechanical energy at any given time is going to be the potential energy, in this case gravitational potential energy, plus kinetic energy. So I can put some things in a calculator here and say, well, my mechanical energy is 196 joules. My gravitational potential energy that I just calculated is 147 joules. So that must mean some quantity of energy has been converted to kinetic energy. What value is that? I can find the difference between 196 and 147, which is 49 joules. So that's how much potential energy, or sorry, kinetic energy is now in this rock while it is falling at 15 meters. Then I can say, well, how fast is it going at that time? I know kinetic energy is 1/2 mv squared. So I can put these values in and say, well, I have 49 joules equals 1/2 times a mass value of 1 kilogram times velocity squared. Solving for velocity, I will divide my 49 by 1/2 and then take the square root of that value, and I get a velocity of about 9.9 meters per second. Now, technically this is a speed, if we think about that, because what is this rock doing? It is falling, right? So notice that if I really did want this to be a velocity, I should make that value negative here. So I have now calculated at time B the kinetic energy, the gravitational potential energy, and the mechanical energy stays the same, and I can now calculate the velocity from that. Okay? And I predicted, to some degree, the relative values of gravitational potential energy and kinetic energy. What's my next scenario? Next scenario is at 7 meters. I'll do that down here. Or over here, maybe. So at 7 meters, my height, at time C, let's make a prediction. Maybe, so we're over halfway down. So maybe we've switched to some degree. Now maybe only a small portion of our pie chart is gravitational potential energy, and a significantly larger portion is now kinetic energy. It is moving way faster, and it has less to fall, so it is now has more energy as kinetic energy than it does as gravitational potential energy. How do I find this out? I can, again, my mass is 1 kilogram. My height, my new height now is 7 meters. And I can calculate the gravitational potential energy at times c by doing 1 times 9.8 times 7, which comes out to be about 68.6 joules. I will round that to 69 joules. That means that if my mechanical energy, again, mechanical energy stays the same throughout, right? The size of my pie chart does not change, the total 100% of it. It's just how much of it is kinetic energy, how much of it is gravitational potential energy. So my mechanical energy the whole time is 196 joules. So that means if my mechanical energy is made up of gravitational potential energy at times c and kinetic energy at times c, how can I find kinetic energy? Well, 196 is now equal to 69 plus some value for kinetic energy at times c, which I can solve by subtracting 69 from 196 to get 127 joules at times c, right? Notice the energy distribution here. A lot more kinetic energy relative to gravitational. It has some, but not a lot, not relative to this. That's a J, by the way, here for joules. How do I find how fast it's going? Well, again, kinetic energy is 1/2 mv squared. If my kinetic energy is 127 joules, and I can put that into my equation. My mass is 1 kilogram. I'm solving for the velocity. Just as before, 127 divided by 1/2, and then square rooted. I would also normally divide by my mass, but my mass is 1 here. Okay? And I get 15.937, and I will round that to about 16 meters per second. Again, it should be negative because I'm falling, or the rock is falling. Now let's look at time d. At time d, it's right before it hits the ground, so we're going to assume our height is now 0 meters, which means that our gravitational potential energy at time d is now 0 joules. It has no more potential due to its position above the ground, because it is effectively not at a decent height above the ground anymore. So that means 100%, if we were to do a pie chart at time d, 100% of our energy now is in kinetic energy. But the total amount of that pie has not changed. It's just 100% of it is now mechanical energy, or sorry, kinetic energy. And so again, our mechanical energy for the system has not changed, 196 joules, and this is now equal to all of our kinetic energy at time d. How fast is it going right before it hits the ground? Well, let's calculate that. It can be, again, kinetic energy is 1/2 mv squared. If all of our 196 joules is kinetic energy, what is our velocity right before we hit the ground? 196 divided by 0.5, and then square rooting that value is about 19.8, so I'm going to round that to about 20 meters per second. And so that is how we have taken our problem here, and we can use the fact that mechanical energy stays the same the entire time to calculate gravitational potential energy or kinetic energy at any given point. Now, again, in this problem, you were given distances the entire time. You could also be given velocities and go the other way around. You could be given a combination of heights or velocities at given points and find one or the other. So the key, I would say, is to find a point where either you have all the information or one value, say at an extreme, the highest peak, the lowest, one value is going to be 0. Here, kinetic energy was 0. Here, gravitational potential energy was 0, right? And so it became a lot easier to find the total mechanical energy and do all of the middle pieces from there.